Okay. Yeah. I
Yes,
don't know. Okay.
so people will probably join slowly. Maybe we should start, Jayon. What do you think?
Yes.
Okay, then I will introduce the speaker. Today, we are starting our seminar for this semester with Professor Anna Geyer, who's an expert in waves in integramal systems, mostly. And she will be telling us, well, she's currently at TU Delft in the Netherlands, a town that's famous for their pottery, right? Resembling Chinese pottery almost, probably because of historical reasons. And she will be telling us about transverse stability of solitary waves in the Camassa-Holm equation. So I'm very curious about this. So Anna, the stage is yours.
Thank you very much, Alejandro. Thank you for the invitation and for the nice presentation or introduction. So what I will talk about today is a collaboration with ULU at Texas Arlington and Dimitri Pelinovsky at McMaster's University in Canada. So this project started when we had a researching team stay in Vienna a couple of years ago, and the final version of the paper appeared earlier this year. And so what we are interested in this research is, as you mentioned them, solitary waves. Those are localized waves. They exist for different equations. For instance, for the Camassa-Holm equation, I will motivate it later in my talk. And we're interested in its stability. And so a lot of stability results exist when you consider just one-dimensional direction of propagation. And then you perturb also the wave in the direction of propagation. So let's say everything in x direction, and you have no y direction. But it's also interesting to study what happens if the perturbation occurs in the transverse direction, so perpendicular to the direction of propagation. And this is what this talk is about. So this is the meaning of transverse stability. I will come back to it. But anyway, just to give an introduction. And so, as I think, at least to the best of my knowledge, transverse stability was first studied for an equation that is called the Korteweg-de-Vries equation. So I want to go back because it's I have a bit more time. It's not a stressful 20 minutes talk. I want to go back to the starting point and start with the Korteweg-de-Vries equation, and actually start with this picture. So maybe you've seen this before. This is a reproduction of a famous experiment by a Scottish engineer called Scott Russell. What he observed was that in the canals in Scotland, they used boats to carry weights and goods, and these boats were driven by horses that, anyway, he saw that the boats, as they approached the canal or went through the canal, pushed a hump of water in front of them, right? The boat goes and the water in front of them is being displaced, and so it pushes like a wave in front of the boat. And then when he saw that the wave kept going even though the boat had stopped, right? And so he observed this wave that was just keep going without the boat in the back, and he went along on his horse and he saw this wave, and he called it the Great Wave of Translation, and this became known as the solitary wave. And then people searched for explanations for this and also for equations which could model such waves, and clearly the just linear wave equation would not be sufficient. And so let's say the simplest equation that can model such a behavior is called the Korteweg-de-Vries equation. It was derived by Korteweg and de Vries a long time ago, 1895. And so if you look at the equation for a moment, the variable is u. It's a function of time and space, in this case just one spatial dimension. U represents, if you want, the surface elevation, but it can also model the horizontal velocity profile. And it has, well, a time evolution part, and then it has two parts. One is a non-linearity, and one is a dispersive part. So dispersive part would normally mean that if you have some localized water, it would just disperse out. And the nonlinear part, if you look at just this bit, this should remind you, for instance, of Burger's equation, you would get steepening effects. Okay, and so as it happens in this equation, those two effects are balanced, right? So the steepening and the dispersing out are at a perfect balance so that it can maintain such a heap of water, as it was observed by this Scott Russell. So it can model these solitary waves, localized waves. Right, so these waves exist. Also, periodic traveling wave solutions exist. This is also of interest, but not for this talk, so I will focus on the solitary case. And then, of course, it was observed that this wave could keep going for a long time, right? So you think that this should be stable. And there are a lot of stability results for this Korteweg-de Vries equation for solitary as well as periodic waves. They can be perturbed with localized perturbations or with periodic perturbations. First results are due to McKean, and then there's famous results by Bona, Suganidis, Strauss, and even still fairly recently, stability result has been obtained by Bernard de Koning and collaborator. So it's still quite active, even though the equation has been proposed a long time ago. The stability results came much later. So this is for one-dimensional solutions. As you can see here, that there's no variation in the y direction. So the main variation, the main thing that's happening is in the x direction, the direction of propagation. And still, we are now curious about transverse stability. So meaning if we perturb along this direction. So in order to do that, we need to allow some y direction, some different horizontal direction. And the first people to derive an equation which would allow to do such an analysis are Kadomtsev and Petviashvili. This was 1970s. So basically what you can see here is you have the same equation as we had before in blue, the KdV equation, but then you have another space derivative on top of it, and you have another term which was not there before, which contains y derivatives. So there's something happening in the y direction. Okay. Our function u now depends on time, x direction and y direction. So, and then here's a parameter that I won't focus on too much, but it's related to surface tension. So when you derive these equations, maybe I should say that Korteweg-de Vries equation and related model equations can be derived from the Euler equations for water waves. So inviscid incompressible Euler equations with mass conservation, conservation of momentum. If you make asymptotic expansions in certain regimes, you get these model equations. And so you can either consider just pure gravity waves when surface tension is small or not there at all, or you can consider a combination of capillary and gravity case. So then you would have surface tension effects as well. And basically, there are two scenarios which are also relevant for the stability analysis. If the sign of this coefficient sigma is positive, so let's say sigma is 1, this corresponds to weak or no surface tension, so purely gravity waves, then one can show that these solitary waves and also periodic waves are transversely stable. Okay, so if we study this equation, basically you study an operator, linearized operator in its spectrum, then you will find that these solutions are stable, transversely stable. These go back to papers by Mitsumachi for the solitary case and Mariana Haraguch and Dmitry Pelinovsky for the periodic case. However, if the surface tension coefficient is negative, so if in the case where the surface tension dominates the gravity waves, things become unstable. And so there are papers by Sakharov, a famous criterion by Rousset and Svetkov for solitary waves, and this is the paper for periodic waves. And these
Anna,
two cases, yeah, of course, please.
If I may, what's the reason for these, for X and Y having such different roles, if I may? Because I always thought that, well, let's say that you have a surface of water, whichever fluid, right?
Yeah.
Why would you pick one direction over the other? Why are they so different?
Yeah, so that's it's not a purely symmetric picture. So in the derivation, I'm not very familiar with the derivation, but as far as I understood, you make a choice that you consider one direction as your main dominant direction, and the other one you allow for weak variations in the other one. So, for instance, this two-dimensional KdV equation or KP equation can model interaction of wave fronts at different angles, for instance. But there is a limitation on the angle cannot be too oblique. So you can only have like small deviations from the x direction. So it's a weak y dependence if you want to.
I see. So somehow there is an implicit bias in one direction. So you're always thinking of these canals somehow.
Yes, exactly. Yeah.
I
Yeah.
see.
You actually, so this is not suitable to really model general two-dimensional waves which we have no limitation in the sense of like there's no dominant direction. But here we are thinking of, well, basically everything is happening in one direction. There's little variation in the y direction, but it could be a bit. So I'm interested in studying what happens if I disturb the wave in this y direction, which is
I see.
not the dominant one. Yeah.
I see. Thank you very much. Thank you.
Yeah, thank you. Okay. So why this was like to introduce the first papers and results on transverse stability or instability, but the equation that I want to study today is not the KdV equation, but another one which is called Camassa-Holm equation. And so that means the blue part in here will change, will be different. Let me introduce the equation first, and then I will tell you sort of what's the difference. I mean, you can see immediately it involves more terms and also higher order nonlinearities, so it's a bit more complicated, which also means that it is richer in the dynamics that it can model. So if you derive the Camassa-Holm equation from the Euler equations, U will now be not the surface profile, but the horizontal velocity profile at some depth inside the fluid. At the moment, this is just a one-dimensional equation, so it just depends on time and one spatial variable. And it's models moderate amplitude waves. What does this mean? The regime in which you derive such an equation is different than that from the KdV regime. So you allow for larger waves. You make a different choice about wave amplitude, wavelength, and water depth. So you can model waves which are taller, which are bigger. This also means that the nonlinearities will grow. So there's this parameter which sort of tracks how tall the waves are is also corresponding to the nonlinearities. So if the nonlinearity in an equation is stronger, it means that you don't necessarily have this perfect balance between nonlinearity and dispersion, which maintains the solitary wave. You can also have situations where this balance is ruined in the sense that you get wave breaking. Okay, so let me say the following. This equation also has smooth solutions like the KdV, so solitary and periodic waves, but they can also be peaked or cusped. So that means that at their crest, there is a corner or even an infinite singularity in the derivative. If you start with initial data, like the initial hump of water is sufficiently steep, and you let this evolve, wave breaking can occur. And this is due to the fact that the nonlinearities are stronger in this equation. But also you can have global solutions. So if the initial data is nice, let's say, things can propagate for long times. Okay, so that's the equation I want to propose. And right, stability of solutions for this one-dimensional equation have been carried out like 20 years ago. So it was shown by a famous paper by Konstantin and Walter Strauss that smooth solutions are orbitally stable. These proofs rely on the integrability property, like inverse scattering and stuff like that. Okay, but since this equation also has peaked solutions, it's also interesting to study the stability of those. So these are the ones with the corner crest. And there it was believed for a long time that they are also stable. Actually, it was an energetic stability result in H1, but fairly recently, Dmitry Pelinovsky and collaborators proved that these peaked solutions are actually unstable. So if you look at the correct spaces, not the energy space, but the space in which these solutions are well defined, so that's W1 infinity, then you can show that these perturbations will actually grow in time. So they're unstable. But that's just
Anna,
a side
I have a question.
of course.
What is the instability mechanism of peak solutions?
Mechanism.
Instability. Why is there an instability when there's a peak? I think peak is like this I mean, like C1 blow up or something like that, right?
Yeah, well, peak is there's a jump in the derivative.
Yes.
Yeah,
C1
okay.
blow up.
And
this is what I
exactly,
said.
yeah.
Okay.
So
And
what they do in the paper, they track as far as I know, they track the position of the peak, right? They understand how the position moves, and they see that it moves at characteristic speed. So they do like method of characteristics, and then they basically, I think it's sort of Burgers type singularity plus some perturbation, which actually doesn't change the blow up. So you can show that the perturbation then grows in time, and that's how you prove it. Yeah.
Okay, thank you.
Yeah. Okay, so but what about transverse stability of this equation? So far, as far as we know, there have only been results on stability in the x direction, so the same direction as propagation. And to study transverse stability, you need again an equation which allows for some movement in the y direction, right? And so this is what our collaborator Leo did. He proposed a model which we call Camassa Holm KP, because it's like the two-dimensional KdV version, but for Camassa Holm. So it's Camassa Holm KP, and it has exactly the same structure as a two-dimensional KdV equation. So in the blue part is the one-dimensional equation Camassa Holm. Then you have an additional space x derivative, and you have this term again. So everything is the same, except u now depends weakly on y. By the way, also this equation was derived in a completely different context many years ago by Robin-Ming Cheng in the context of elasticity theory. A bit more general equation as far as I know, but so here by Leo it was proposed as an equation for water waves. So let me tell you a bit about what they do in their paper. We will need a few things, namely the space in which solutions exist. So they have a local hypotenuse result in a space that they call XS, where this is basically a Sobolev space HS for s greater than 2, where the function, the derivative, and the antiderivative are in this HS space. The antiderivative is defined like this for functions which decay at plus infinity, and they're allowed to oscillate or mildly grow at the negative infinity. And what they also do in their paper, but I won't go into detail, is they have some wave breaking criteria as well. What we do need, and what they show in their paper, is that the equation has a Hamiltonian structure, right? So you can write this equation as an evolution equation in Hamiltonian form. So if you have a look here, for instance, the terms which involve time derivatives are these two. So that's basically ut and an operator 1 minus del x squared. So this operator here, right? So you can put this on the other side, and then you can write it in evolution form. You have this operator j, which is very classic in this type of problems. It's a skew symmetric operator. And then you have conserved energy, Hamiltonian energy, and the derivative thereof. This evolution equation in this form is called a Hamiltonian evolution equation. And just maybe to note here, the F energy looks exactly like the one-dimensional energy. So the same Hamiltonian structure is true also for Camassa Holm in just one dimensions, except that you don't have, my mouse doesn't, you don't have this term here, which involves the y derivative, obviously. Otherwise, it has the same structure. And there are two more conserved quantities, momentum and mass. They are also identical to the one-dimensional version. And we will use this Hamiltonian form and the conserved quantities a lot, as it's not unusual in stability problems. Okay, what about solutions for this equation? Well, as you can see directly from, if you look at the equation and you assume that your variable u does not depend on y, then this term will just drop out, right? And you can integrate once and you would be left with just a general one-dimensional Camassa Holm equation. So trivially, all the solutions which are solutions of one-dimensional Camassa Holm equation will be solutions of this two-dimensional version, just with no variation in y. Okay? So you get for free existence of the solutions just by extending, all the traveling wave solutions of the one-dimensional Camassa Holm, that let's denote them by phi. They're moving in this moving frame of reference, x minus tc, where c denotes the wave speed. So you just move along with the wave along the canal. And there's no variation in y, so they're just constant. These are sometimes called line solitary waves, right? Because there's nothing happening in the y directions. And I want to mention, just not relevant for my talk, but because of interest, there is now a very recent result on non-trivial, or let's say, non-trivial three-dimensional waves, which is basically a solitary waves with some periodic modulation in the y direction. This is a very recent result by Douglas Nielsen and collaborators, where they use a version of the Lyapunov-Center theorem to prove this. So here they have some variation in y, but okay, that's not the topic of the talk, but still interesting for everyone to know that this equation admits also non-trivial three-dimensional solutions. So for me, I will focus on these ones, these line solitary waves, and I'm interested in perturbations in the transverse direction. So now I think I will, before I go to the results, I will give some background on what is to be expected, okay, for this and other equations. So some results on transverse instability, actually for the full water wave problem, because after all, we are studying model equations, but they always come from the full water wave problem, right? And what we are eventually interested in is the full water wave problem. So what is already known for gravity capillary and gravity water waves in the periodic case, so there has been, that's an older result by Rousset and Tsvetkov for the solitary case, by Haragush, Eric Wallin, and his former PhD student, and the very recent results by Walter Strauss on steady gravity water waves, showing that they're actually transversely unstable. For the KP equation, so that's the KdV version, two-dimensional KdV version, in the case where the surface tension is strong, so this KP1, solitary and periodic waves are unstable, basically. And even there's a fractional KP version where you have fractional derivatives, they also prove this instability. And there's a very recent result where they pass this linear instability onto the full nonlinear instability. And then there's a paper which is related to, this is the equation that we are studying today, but with a different sign. So this is a negative sign in the sigma. They proved that solitary waves are unstable in this case. So let's go back. If I have a negative sign here, they showed that these things are unstable. This is Robin-Ming Cheng with his former PhD student. In the case of stability, there's a very recent paper by Frédéric Rousseau and Xun on solitary gravity water waves showing stability. Then we have solitary and periodic traveling waves in the KP2, so that's the KdV equation with a positive, so weak dispersion. I think I mentioned those results before. This paper I want to mention because what is the BKP family? So also let me go back to the equation. Maybe some of you know that the Camassa-Holm equation actually belongs to a whole family of equations, the so-called B family equations, of which only two are integrable, the Camassa-Holm and the de Gasperi-Procesi. But the parameter B would go in here, so this would be B plus 1 here. And then you can study the stability properties for the entire family. And they did that. So this is also Robin-Ming Cheng and collaborators performing spectral analysis of, actually they have stability and instability results for periodic waves. Okay. And what
I have a question. I forgot to make sure.
Please.
So whenever you say stability, is it nonlinear stability?
Not always. So some of these results are linear stability, and very few are nonlinear stability.
I see.
So, for instance, this paper is linear, spectral. Actually, they have a very complete study of the spectral analysis.
So most of them are linear stability.
Most of them are linear stability. I know that this one, for instance, is nonlinear. Let me see if I know from Mitsumachi has, I think, also passed it on to nonlinear stability. Here, this one I'm not sure. So most of the results are on the linear level, and we will also today talk about linear or spectral linear stability.
Okay.
So passing to nonlinear stability is often very difficult and delicate, right?
But I learned that some people use a Twinbroom's pointwise estimate, or there are several. Okay, I know it's delicate. I know it's there, but okay, linear stability. Thank you.
Yes, thank you for the question. Okay, so yeah, I will discuss now what I mean exactly by linear stability, right?
Yeah.
So now this is the result that we want to present today. Solitary waves, these line solitary waves, for the Camassa-Holm KP equation, so two-dimensional Camassa-Holm equation, in the case where there is no surface tension, so we have a positive sign. So what do I mean? U is a solution of the equation, and I decompose it into a part which is the traveling wave part, which has no variation in y, and it's moving in moving frame. And then I have a perturbation, which is moving along with the traveling wave, but it is allowed to vary in y and t. Okay. If I plug this decomposition into the Hamiltonian form of the equation, and I cut everything out which is nonlinear, so I truncate at leading order, I get this equation, which is a linear equation or linearized equation for the perturbation. So we're trying to understand what does the perturbation do as time evolves on a linear level. So the way I'm writing this is the following. I have two separate parts. One part does not include any y derivatives. So this is the part that is the same as for the one-dimensional Camassa-Holm equation. And then I have the part which contains y derivatives, which is the new part, which is transverse stuff. The operator J we had seen before. This was this Q-symmetric operator. And L is this operator. This involves the traveling wave phi and derivatives. And you can see that this is a Sturm-Liouville operator. It's definitely a self-adjoint operator. Okay, it's well behaved. Anyway, we'll touch this on the next slide or so. So what do we mean by stability? If we make an ansatz where we separate variables t, y, and x in this way, then we arrive at the spectral stability problem. This is a very classical way of doing things. So I'm highlighting the part which is new in the sense that it corresponds to transverse stability. The eta, you should watch out for the eta in green always. This is where the transverse stability happens, right? Eta is the parameter which checks the transverse direction. So if the green thing is not there, there's no transverse direction, then everything is well known, let's say. Then we only have the one-dimensional Camassa-Holm part. So I'm moving to the next slide. This is the spectral problem. And so our one definition of transversally stable could be a solitary wave is transversally spectrally stable if for any eta, the parameter measuring transversality, there are no eigenvalues with positive real part, because positive real part would correspond to growth in time. So we don't want that, right? So that means the spectrum is in the negative half plane. If you have that, then you have spectrally stable solitary waves. Okay. So
I
it
have a
turns
question.
out.
So sorry, Anna.
Yes, please.
So the spectrum consists of eigenvalues only, or are there continuous spectrum?
Sorry. Yeah. No. There can be continuous spectrum. Of course, you're right. Yeah, that's actually not a good way of writing this. So just look at this.
Okay. Clear.
It could be eigenvalues or there will be continuous spectrum, of course. So that's true. I should not write this. Yeah. So just the spectrum is contained in the left half plane. Then you would have stability, spectral stability. And it has proven advantages in the past for other authors, and we are following this route to not work. So this is the spectrum in L2, right? But it proves to be advantages to work in a weighted L2 space, actually. So let me briefly comment on this and why we do this and where we have this idea from. There's a paper by Pego and Weinstein on the Korteweg-de Vries equation, where they study asymptotic stability for Korteweg-de Vries. And they use weighted L2 spaces. The reason is the following. They're interested in long-time asymptotic behavior of a solution when they perturb a solitary wave. They hit it, and after a while, they see that the main dominant solitary wave emerges at the front. It may be followed by a smaller one, and then definitely there's some radiation, decaying radiation at the back, which is traveling actually in the other direction. So when they study this stability of these objects, they need a norm in which sort of this dispersive decay tail is being eliminated. And so that's why they introduced this weighted space. So you have a function is in such a weighted L2 space if the function times an exponential with some weight mu is in L2. And you have a corresponding L2 norm for this. And what happens, for instance, if you just a quick calculation can show you that any function which travels to the left, so these things here, will, in this weighted L2 norm, will give you the L2 norm of f times this exponential decay. So it will just die out. And this is the norms that they were using. And we will see that using such weighted norms are also very good in our problem, especially when we are looking at the continuous spectrum. So we will see that in a moment. So actually, this is the definition of transversal stability that we are using, and it's actually stronger than the previous one, so it implies the previous one. So asymptotic transverse stability means that for all eta, there exists a positive constant b, such that the entire spectrum of the operator is included in a left half plane, to the left of minus b.
But Anna,
so strictly away from zero.
Yeah.
Yes.
But do you also need the zero eigenvalue to be algebraically simple?
I will come to that. Yes, you will see that.
Okay.
It's
Thank
actually
you.
geometrically simple and algebraically double.
Yeah,
I will see.
algebraic double. Sorry. Yes, thank you.
Yeah. Okay. So going back to, let's start, right? We have the one-dimensional Camassa-Holm equation. The solitary waves of this form are known to exist. This has been done, for instance, by Jonathan Denels. They exist for all wave speeds greater than 3k, where k is the asymptotic value that the solitary waves decay to at infinity. And then it makes sense to shift the waves such that they decay to zero. So the psi is our shifted solitary wave where you have decay to zero, as it is sketched here. Important for us is the fact that then this psi satisfies a first order invariant. So basically you can multiply by phi prime once and integrate again, so you get this nice invariant. And what else do we need? We need exponential decay, symmetry, and monotonicity. Those are some properties that are relevant. And these profiles, these solitary waves, can also be characterized in terms of, they have variational characterization. So we can write down an augmented energy. So that's like the Hamiltonian energy, and you augment them by using the other two conserved quantities that we have, right? So maybe just to point out why I put the hats here, it's not really very terribly important, but the hat differs from the non-hat version in that we have to subtract a constant, which is the one that decay at infinity, otherwise these things wouldn't converge. And also here I'm not including the y derivative, so this is purely one-dimensional stuff. If you have this augmented energy, then the traveling wave is a critical point of energy. Okay, so the traveling waves will be a critical point of this energy. And the second variation, so if you look at the second variation of the derivative, this gives you exactly this linear operator L that we had previously in our formulation. So this L. Yeah. So this is the second variation of this energy. So when you do analysis on just one-dimensional Camassa-Holm, usually you study the spectrum of this operator. If you think back of in functions, you want to prove that something is a minimum of a function, you compute the second derivative and check that it's negative, right? Then you would know it's a minimum. So similarly here, you want to show that this has negative spectrum, and then you need some more tools to show that also JL would be well behaved. Anyway, side note. What we need is something that is not unusual in stability analysis. The fact that these conserved quantities, if you view them as functions of the speed, are monotone. In this case, they are monotonically increasing. So for instance, in the famous paper by Konstantin and Strauss, where they prove orbital stability of Camassa-Holm solitones, this proof goes through because the E, I think, momentum is monotonically increasing with the wave speed. And we have something similar, and we need this a lot. The way to prove this is using this first order invariant, and you rewrite the integrand, and you change variables, and you make some explicit computations such that you know that if you differentiate this with respect to C, which is not obvious how you would do that, right? Because psi is just implicitly depending on C. So it's not, so that's some calculations, but you can prove that they're increasing, and you will see in a moment where this comes in. Okay, so I will recall a few things that are known about the operator L from the one-dimensional Camassa-Holm analysis. So this is the nicest scenario that you can think of. You have a self-adjoint Sturm-Liouville operator, right? And then you have a lot of information. You know that the eigenvalues of this operator are real, they are simple, they can be ordered in a sequence, and importantly, this sequence is such that the eigenfunction of the nth eigenvalue has n-1 zeros. Okay, this is a well-known result, and this is being used a lot. You will see how in a moment. So what do we know about the continuous spectrum of this operator? Because we have exponential decay of these solitary waves, we can use Weis' theorem to tell us that the continuous spectrum of the operator is actually the spectrum of the constant coefficient operator, which is obtained when you let x go to infinity. So here phi goes to k, some constant at infinity. So you replace phi by k, you get this constant coefficient operator, of which you can easily compute the spectrum. So then the continuous spectrum of this is just the spectrum of this operator, and we know this constant here is strictly positive. This was the condition for which solitary waves exist, which means that the continuous spectrum is away from zero. There is a gap between a potential zero eigenvalue and the continuous spectrum, which is often used or needed. So you are asked about the zero eigenvalue. This is almost always the case in these equations. There is some invariance, for instance, due to translation. You can translate the solutions, and this translation invariance causes an element in the kernel of L. So you have a zero eigenvalue. And then you do the following analysis. Phi is the solitary wave. It has exactly one maximum. So phi prime will have exactly 1, 0. And now I'm using this sentence. Phi prime has 1, 0, so it means n is 2. Phi prime corresponds to the second eigenvalue, and that means there must be one more eigenvalue before, which is, well, if 0 is the second eigenvalue, it must have a negative eigenvalue. So this is the spectral picture of this operator L, which is being used also in the stability analysis for the one-dimensional Camassa-Holm equation. But what we are interested in, let's go back to the operator that we're interested in, is this one. So this is the spectral problem that we have. So we have JL, not just L, and we have the transverse part. Okay. So we know L, and now what happens when we add J? And we look at the spectrum of JL in L2. Still, phi prime will be in the kernel. And when we look at the continuous spectrum, it will also be quite similar. So let's say this is the part that corresponds to just the L0 part, and here this one corresponds to this operator J, right? And if you compute that and you look at what this gives you, it tells you that the continuous spectrum is located on the imaginary axis. Okay, that's not too bad. And since we know already that Camassa-Holm equation is spectrally stable, even orbitally stable, we know no more spectrum exists anywhere else, right? So everything is on the imaginary axis, the continuous spectrum and potentially any other eigenvalues. So, but what happens if we don't look at L2, but we look at the weighted space? I mentioned before that this is an advantage, and now I'm going to show you why. If we look at the continuous spectrum in the weighted space, what happens is that it bends away from the imaginary axis, and it actually also shifts away from the imaginary axis. So it's not easy to see here, but zero is now an isolated eigenvalue, and the continuous spectrum has shifted to the left, to the stable half plane. Right? This can be done. I'm showing a picture because it's nicer to see, but you can just calculate this explicitly and prove it. So this is good news, right? Because we're moving into the stable plane. So if you want to prove stability, that's good news. And 0 is still an eigenvalue. but we have not touched anything in the transverse direction yet, right? I have not included any green parts yet. So our task is to include the green part. Sorry, I should mention first that you asked about the eigenvalues. Okay. So 0 is an eigenvalue, right? Because of this translational invariance. And I claim it has geometric multiplicity 1. So it's spanned just by phi prime. This can be shown by some Wronskian argument. You have a second order differential equation, so you have to exclude that there's another solution, and you show that at infinity you have a 0 Wronskian, and then the second solution would have to exponentially blow up, and it doesn't. So you can show that it's spanned by just phi prime, and the 0 eigenvalue has algebraic multiplicity 2. To see this, you compute, or this is known actually, that the C derivative of the solitary wave is a generalized eigenfunction, so it satisfies this inhomogeneous equation. So in order to show that it has not higher algebraic multiplicity, we need to show that there exists no f, so this inhomogeneous equation doesn't have a solution, right, where I put the del C phi on the right-hand side. And in order to do that, you basically use Fredholm theory. This inhomogeneous equation would have a solution if the right-hand side in the inner product with the element in the kernel would give 0. So if I do that, I put the right-hand side in the inner product with the element in the kernel, which we know is phi prime, and I compute the inner product, and then out pops this quantity. Okay, and this is the energy or momentum differentiated with respect to the wave speed. And we have proven that this is strictly monotonically increasing. So in particular, it's non-zero, right? And so we get that this thing doesn't have a solution. So we can prove that algebraic multiplicity is exactly 2. So this is the first instant where this monotonicity comes into play.
So Anna, can I make sure?
Yeah, sure.
So it seems that this monotonicity is so crucial. If this monotonicity doesn't hold, then there's no analysis.
We use it in several places. Yes.
Wow.
Yeah.
So in some sense, this is so lucky. Or you already have some intuition why this monotonicity holds.
Yeah, I mean, it's not surprising because it's in the one-dimensional analysis. It is also crucial. So I don't know if you know this famous paper by Grilakis, Chattah, and Strauss to prove orbital stability. They have a huge abstract machinery which many people use to prove orbital stability, and you show that often the operator does not have purely negative spectrum. There's some unstable direction, but you can usually remedy this unstable direction by if you know that this monotonicity property holds.
Mm-hmm.
So this appears, and so it was not completely surprising that such a property would be needed. Yeah.
So okay. So are you saying that this is really because of it's a one-dimensional solitary wave? If you consider two-dimensional planar wave, then there's no such monotonicity. Or...
Yeah. We have the monotonicity as well in the two-dimensional case. Okay. I wanted to say that it was not surprising because it's also used in one-dimensional.
Okay, cool. Thank you. Thank you.
Yeah, sure. Okay, so this is just a summary of what we have. Spectrum in L2, everything is on the imaginary axis. Spectrum on the weighted space, everything shifts from the imaginary axis into the stable half plane, and the eigenvalue is now isolated and double. And so now I'm adding the transverse direction. So green parts appear, the eta appears, this is the transverse direction, and our result is the following. The continuous spectrum of this operator, including the transverse direction, is given by the range of some function, which you've seen before, right? This is the J part, this is the part of L, and this is the part of the transverse direction. And we can prove that it has strictly negative real part. So it looks like this. The green curve is the one where we add transverse stability. So it's nice, it moves in the right direction, even further away from 0, and at least the continuous spectrum would not cause any instabilities. Okay. What about the 0 eigenvalues? We should be cautious, right? If we have a double 0 eigenvalue in 0 and we add this transverse perturbation, they could split, right? And where do they go? So this this, yeah, I said so. Isolated double eigenvalue can split once eta is different from 0. And what we show is that they split also in the nice direction. They split into the left plane. In order to prove this, we use a perturbation argument. Okay, so because the 0 is isolated, it's algebraically double and geometrically simple. And because the eigenvalues are continuous in the parameter eta, we can do such a perturbation analysis. Basically, what we do is we expand the solution of the spectral problem in the vector as well as the eigenvalue in terms of eta. Okay, we write down the expansion, and basically you get a spectral problem at each order of eta. So this is what we have: 0 order, eta 1, eta 2. At each order you get a spectral problem, and then you start from the top. Here you can still say something, right? I know what is this element. Well, this is just phi prime. This was the corresponding to the translation invariance. Also phi v1 I can compute because this was the generalized eigenvector. At order 2, I have to be a bit careful and I have to start working. I rewrite it in a clever way, and then in order to prove, to check whether this has a solution, I have to check the Fred-Holm condition again for solvability, and look what comes out. Lambda 1, the condition for lambda 1 such that this has a solution is this. Again, in terms of the monotonicity of the momentum. So this is strictly negative because we know this is monotonically increasing. And okay, what does it mean? I have a lambda 1 squared is negative, so this will give me a complex number, right? So lambda 1 is a purely imaginary number. At this order, at least, the eigenvalue splits up along the imaginary axis. Let's go to the next order. Similar thing, more complicated analysis is horrible expressions, but you can do it. And here you okay, the notation doesn't match. This is from the paper, I'm sorry. But anyway, you take the mass and the momentum differentiated with respect to the wave speed, and we know that both of them are monotonically increasing. So you can simplify this stuff and show that lambda 2 is negative. So that means at the next order, things move into the stable plane. Okay, so this is just to give you some idea of how these proofs work. So basically, until now, this is what we've done. Okay, we have shown that the spectrum of this operator, including transverse direction in the weighted space, is moved into here. So it's this green curve. We can prove this is strictly negative, and we prove that the double 0 eigenvalue gets perturbed into this complex conjugate pair, which has negative real part. So at this point, what you would like to conclude is, great, no? Then we have stability. But what we do not know is whether there are any other eigenvalues of Camassa-Holm which are hidden on the imaginary axis, which we did not know, right? We only know that there was a continuous spectrum along the imaginary axis, which is pushed into the left, and we know that there's a 0 eigenvalue. But it could be that there are more eigenvalues somewhere here in L2, which when you pass to the weighted space, they become isolated, and then when you add the transverse perturbation, they could move into the right plane. This is not, for instance, for the KTV equation, such a scenario has been ruled out. Exactly in the paper by Pego and Weinstein about asymptotic stability for KTV, they showed that there are no further isolated eigenvalues along the imaginary axis. So you can conclude on transverse. You could conclude on transverse stability for the Korteweg-de-Vries case. But in the Camassa-Holm equation, I know that there's a group of people working on this right now. So by private communication, it has been indicated that probably very soon there will be a result in which those red bits can be ruled out, and that would allow us to conclude here on transverse stability for arbitrary amplitude solitary solutions for Camassa-Holm. But until we have that result, we are not able to conclude at this point. So I want to shift now. I think I have a few more minutes. Is that okay?
Yes, you should still have like 10 or 15 minutes.
Okay, fine. So at this point, are there any questions at this point? Because then now I will move to a small amplitude case, and and showed that we have stability for the small amplitudes.
Excuse me. I have a question. Oh, I'm sorry. I have a question about this point you just mentioned.
Jensik,
There's-
you have echo, I think, that you have maybe two devices close to one another.
I will ask the question later after fixing the problem.
Okay. So I think Jensik will ask later.
Maybe let's ask the questions after when I'm done and figure out the echo in the meantime. Okay. So I cannot conclude at this point. So what we will do is we limit our attention now to small amplitude waves. So what does this mean? Remember the solitary waves which were shifted so that they decay to zero, they would call them psi, and their maximum amplitude are c minus 3k, which is strictly positive. And so we will use this number as our small parameter, sorry, epsilon, actually the square root of that. So this will be our epsilon. We will take it small, which means we have small amplitude. If we do that, then we are able to conclude that the entire spectrum of the operator JL plus the transverse part, not just the continuous part, right? The entire spectrum, so it could contain any eigenvalues, are contained in a left half plane where there's some is small in terms of epsilon. The double eigenvalue which splits into a pair are not, they might be somewhere else, but they are definitely in the left half plane as well. So from this spectral conclusion, we can say that small amplitude solitary waves are transversally stable in the weighted L2 space. So this is a weaker result in the sense that we have to limit ourselves to small amplitude waves, but it is a complete result, so there cannot go anything wrong. How to do that is basically doing resolvent estimates. So, well, there's two ingredients. Mostly resolvent estimates. This is quite usual, as I understand in this business, that you consider separately a high frequency and a low frequency region, depending on whether the transverse parameter eta is large or small. And the second key idea that we are using is asymptotic reduction of Camassa Holm Kp to Kp. What do I mean by that? You can think of, I mean, if you don't think about this, the transverse direction, just the one-dimensional equations, Camassa Holm is like an extended version of KdV, right? So you can sort of think that the solutions and the equation can be reduced on some level when you make some perturbation and you exclude higher order terms, you can go back to the simpler equation. And these sort of asymptotic reductions have been used in the past for stability analysis. We are going to follow a paper by Mitsumachi, where they study the Benny-Luke equation. Benny-Luke equation is also an equation in water waves. And they prove transverse stability for the Benny-Luke equation, and they use that it can be reduced to the Kp or two-dimensional KdV equation. I think I've seen such an asymptotic reduction also for the gravity water waves, where they reduce it to Kp. So people do this, and it's very useful. So what do I mean? It's the following. I shift to a different set of variables. So these are my new variables. We call them the Kp variables. And then I consider a perturbation of the asymptotic background state K. I plug this into my equation, the Camassa-Holm Kp equation, and I truncate everything at epsilon equals 0, and out pops the Kp equation. Magic. So, or maybe not, right? Maybe it was to be expected. So this is the KdV equation, and so the other things are the two-dimensional version. So you can reduce in the right scaling from Camassa-Holm Kp back to Kp. And you can also prove that the solitary wave solutions of Camassa-Holm can be written as a perturbation of the solitary wave solutions for KdV, right? So every solitary wave of Camassa-Holm is take the solitary wave of KdV and perturb it by something bounded. The solitary waves of Camassa of KdV are well known. They're explicitly written in terms of this Z-squared solution. So this you have to prove, but you can prove this using some implicit function argument. Okay, and so now knowing this asymptotic reduction and knowing this this scaling, this KP scaling, I can write my spectral problem in terms of these new variables, which allow me to decompose the operator in a KDV part and a perturbed part, right? The Camassa-Holm part. And the green part is always the transverse stability. And notice now the transverse parameter eta has turned into epsilon, just because of it also is affected by the scaling. And the little lambda, our eigenvalues, the spectral parameter is now capital lambda. Okay, and we also have to rescale the exponential weight, but that's not so important. And so I will be very brief because this becomes very technical, and I think we should not put too much technical stuff now at the end of a talk. Basically, you write in these new scaled variables the spectral problem, and you get a resolvent estimate. This function here should remind you of the spectral function that we used in the first part of the talk, which gave us the continuous spectrum. And so it's a constant coefficient operator. You can just use Fourier transform, and you compute that this is the resolvent estimate that you get. If you go back to the original variables, you write the resolvent equation like this, where you have sort of 3 parts of which you do different analysis. So for instance, this part here, you know that is small because where you use this KP scaling. Then you get these sort of bounds on parts of this operator, and you use a resolvent identity. So this is what we want to bound, and you know that this is equal to this. This bit is bounded by this, and if we know that A2 is small by this estimate, then this is a near identity operator and can be inverted. So you have all kinds of analysis like this, and I mean this is too technical, but you can split it up into smaller problems and arrive at your resolvent estimate. It tells you that lambda with real part greater than something and eta sufficiently large. The resolvent equation has a unique solution, so that means it's in the resolvent, it's not in the spectrum. So that means the opposite direction would be the elements that are in the spectrum. So they are to the left of something negative. So they are stable spectrum. And similarly, for the low frequency, okay, you have to check what happens to the eigenvalues, right? And then it's also interesting, the pair of eigenvalues that we had before for the Camassa-Holm KP equation, they are actually the same as the pair, at least in the expansion, they agree with the eigenvalues of the KP equation. So if we compare the exact expression of the pair of eigenvalues for the KP equation, this has been studied in some paper, this is the result that they get. And if we look at our eigenvalues that we computed in the KP scaling and we compare the two, then we see that they are identical, at least at first orders. So this gave us the idea that we should be able to prove this rigorously and for any transverse direction that these KP eigenvalues are near the Camassa-Holm KP eigenvalues, epsilon close. Okay, so yeah, I don't want to mention this much. You write the scaled spectral problem and you take away the perturbations, and then you know that the KP eigenvalues solve this truncated problem, and then you use some Lyapunov-Schmidt reduction to prove that the perturbed problem also has a solution. And now finally, last slide, so the resolvent equation for the low frequency case, so that means small transverse direction. You also get, if the real part of the spectral parameter is bigger than some negative small number, you get a unique solution of the resolvent equation. So vice versa, the values of the spectral parameter which are less than this negative value belong to the spectrum. So you get stable spectrum. And here again, we use an idea similar to the paper by Mitsumachi on the Medley-Luke equation, and we use that the eigenvalues are near the KP eigenvalues, and we use smallness of the amplitude. Okay, but this is too much detail, so I know that I just wanted to give you a flavor for the analysis is very different. Once we move to the small amplitude case, we basically have to do a lot of calculations using irresolvent identities. Okay, so that's what I want to say. I will quickly summarize. we studied transfer stability of these line solitary waves for a two-dimensional Camassa-Holm equation. In the first part, we showed that the zero eigenvalue splits into a pair of stable eigenvalues once we have transverse perturbation, and the continuous stable spectrum is moved away from the imaginary axis into the stable part. This is for arbitrary amplitude. This does not allow us to conclude yet because there could be isolated eigenvalues which become unstable. So we moved to small amplitude solutions, and we did resolvent estimates and asymptotic reduction of the Camassa-Holm Kp to the Kp to provide spectral stability for small amplitudes. That's all I said about today, and that's all I know. And now I want to conclude with some open problems that we are thinking about studying. So I might share with you. I mentioned already, this is probably the first item on the agenda. We want to exclude that these things happen. We want to be able to conclude transverse spectral stability for arbitrary amplitudes. So if we can show that the spectrum of the operator JL has no embedded eigenvalues, this would give us this result. Of course, it would be interesting to also extend this result to nonlinear transverse stability. We have not done this yet. I know that the paper that we've been following by Mitsumachi, they provide some ideas about how to move to the nonlinear stability result in the Benny-Luke equation. So that could be something to look into. One could look into. Something that I'm very intrigued about personally, but I have not been able to resolve is the following. You know that peaked solutions exist for the Camassa-Holm equation, and therefore, trivially, line peaked solutions exist for this two-dimensional Camassa-Holm equation, right? So they are solutions, this is known. And as far as I know, this equation is the first one which would allow one to study transverse stability or instability of such peaked line solitary solutions. So it would be very interesting to understand this problem. And I don't think that there exists another equation for which this could be done. So that's why I think it would be a very suitable equation to do that. And lastly, I mentioned in the introduction, the two-dimensional Camassa-Holm equation, U, the variable U, represents the velocity field at some depth inside the fluid regime and not the free surface. And I know that there exists an equation, so it would be interesting to derive an equation for the free surface in this 2D case, and then to study stability or instability properties of solitary waves for this free surface equation. And of course, there are many more problems, existence of non-trivial three-dimensional solutions and whatnot, but I had to limit myself. So I will stop now. Thank you very much for your attention, for your questions, and please let me know if you have any further questions. Thank you.
Yes. So let us thank Professor Geyer for a very complete introduction to a vibrant and new topic. And now, if it's all right, we will open the questions to the audience. So feel free to open your microphones and ask whatever you wish, essentially.
Hi, thank you for your nice talk. I have a question about the picture. Hi, I'm Junshik. I have a question about the picture. About you mentioned there may be some possibility of some.
Yeah.
Yes. Yeah, this one. But you mentioned in 1D case, Camassa-Holm case, if you introduce the weighted exponentially weighted norm, then there is no other spectrum on the imaginary axis except zero, right?
I said that the spectrum of Camassa-Holm in L2 is just on the imaginary axis, yes.
Yeah. So I mean, in the exponentially weighted space,
Yes. Where was this? Here. Is this what you mean?
Yes. So in this case, zero is
okay. I think
origin is the isolated eigenvalue, right? This means
so in the exponentially here. Yes, here zero is isolated. Yeah.
Yeah. So continuous spectrum, essential spectrum is separated from. I don't know. Zero eigenvalue is separated from the continuous spectrum in this case, right?
Yes.
Yeah. So is it true for all speed C? or just for small amplitude solitary wave?
No, this is true for all. This is true for all.
Okay, then next, then if you consider, in this case, if you consider the transversal transversal
Yeah.
problem, the 2D problem, then there's a
Yeah.
parameter eta, right, which corresponds to y direction.
Yeah.
And then and because so when eta is 0, it's just origin, and when eta is not 0, it's just parameter. The 0 eigenvalues now it's parameterized, right?
Yeah.
Yeah. So
This is so as soon as eta is non-zero, you have this.
yes. So I think in this situation, I think there is no possibility we have some the situation you worried. Yeah. So, of course.
But the problem is we don't know if there are other eigenvalues on the imaginary axis if there is no eta.
Yeah, but when
So
eta is
in this case, it could, like for Camassa Holm, we know that the entire spectrum is on the imaginary axis, including a zero eigenvalue. But potentially there could be an eigenvalue somewhere here on the imaginary axis that we don't know.
Yeah, but if you introduce exponential weighted norm, you said that there is no other eigenvalue on the imaginary axis except 0, right?
That I don't know. I only know in L2. I only know in L2.
Okay. I see. Okay, so yeah, I see. Okay, thank you. And you obtain some relevant estimate to show some spectral stability in weighted space. So do you also obtain the uniform relevant estimate?
Uniform in
lambda on the right, because you in the paper written by Mizumachi about the Benji-Luke equation, they also obtained the uniform bound of uniform relevant bound in lambda, so that they can conclude it's a linear stability modulo the spectrum near 0, right?
Yes.
Yeah,
Yes,
so
it's like in their case, yes.
Yeah, so I was wondering if you also obtain such a result.
We obtained the results that I showed you, so that's
just the spectral stability?
Yes. Just those results. Yeah.
Okay. I see. So is it difficult to obtain the uniform relevant bound? I mean, what I mean by uniform is uniform in lambda on the right half. Lambda is the real part of lambda is the positive.
This one, right?
Yes.
Yeah. But the uniform.
So here C may depend on lambda, right? No? Is it uniform in lambda?
C, this constant you mean? Yeah. No, that depends on lambda. That's true. Yeah.
Really? Okay. Then, so is it difficult to obtain? Have you tried to obtain the uniform constant C?
I do not think so, actually. So I must say I'm not entirely sure. I must say that at the end of the project, I went on maternity leave, and actually my collaborators worked out the last results and estimates without me.
Okay.
So I don't know.
Yeah, I see.
But it would be interesting to compare with the paper. If you know that paper by Mitsumachi well, then you will be it would be easy for you to follow what we did and to think about this.
I never read this paper.
Okay.
Yeah, but such kind of strategy is even in 1D case, it's quite the common strategy. So because you in the last slide you mentioned about your future project on the nonlinear stability. So the first step is to obtain the linear asymptotic stability. So
right.
Yeah, so that's why I asked.
Yeah. No. That's true. That's the first step in that direction. So no, we have not done that yet. So it's completely. I mean, yeah. still open, and we're interested in doing that. Yeah.
Yeah, oh, okay. Thank you. Thank you.
Yeah. Thank you for the question.
Yes. So maybe I will ask a very naive question, because I come from
Sure.
a background where linear and nonlinear stability are essentially the same. So
Okay.
I essentially know OD. So my question
Yeah.
is, if there is an interpretation for this notion of linear stability in these kind of equations, in the sense of maybe it determines the stability within a certain invariant submanifold or something like this, or is it just a functional analytical statement? That's my question.
As
So
far as I
is there
know,
sort of
as far as I know, the passing from linear to nonlinear is a highly non-trivial matter, and it depends directly on the type of nonlinearity. So it has to be studied individually for each case. At least I don't know of any package or black boxes. So
Yes.
yeah.
But I'm trying to sort of wrap my head around the notion of,
Yeah, sure.
of how this linear stability could have sort of dynamical implications, right? So yes, is there a theorem along the lines of, yes, it determines the stability not on the whole space, because that's very difficult, but maybe within some nonlinear subspace that's fine. I really don't know how to pose it.
Yeah, okay. I'm trying to understand your question. Like, I think it's a really cool question. I don't think I've. So normally, what you do when you pass from linear to when you try to prove nonlinear stability, you restrict the space to some subspaces on which you still get stability. So you have some unstable direction because of some negative eigenvalues or also positive eigenvalues, which you want to rule out. And you can, for instance, when you say yes, modulo translations or modulo elements orthogonal to the kernel, if I eliminate those directions from my space, then then things are stable. So that goes a bit in the direction of what you're saying. At least that's how these nonlinear stability proofs work a bit.
I see. Yes, I think I should think about it a little bit longer. But maybe somebody else has additional questions.
So let me continue. So Alejandro and I, we are from the community of diamond system and also Panabai PD unbounded domain mostly. So that's why whenever we have a spatial stability, it automatically implies nonlinear stability. Okay. But in your case, traveling wave, solitary wave, there's no such direct implication. So, but of course, Alejandro and I, we always expect that if you have some solution which are already linear stable, it should be nonlinear stable. So that's why I am interested in the instability mechanism. Okay, for me, this is a little bit unusual and exotic to me. Yeah, but now I have a question because indeed, as a ODE guy, Parabolic PD guy, ODE guy, I learned a lot of this. Your the knowledge about your talk from Jinsik. And whenever I discuss with him, I always has a complaint about why do people introduce the exponential weight? And of course, there's an issue of this spectral gap because the spectrum is on the real, immediate axis. But okay, then my first question to you is, can you prove some stability or instability result on the L2 space directly? Is that possible?
I don't think so. Like for instance, this perturbation argument, you would not be allowed to do to split the eigenvalues to check. You would not. I don't think you can do that if it's embedded in the continuous spectrum.
Yeah.
And yeah, I think that's definitely would be an issue.
Yes. And I want to give you information, which is I don't think it's whether it's true or it's applicable in your case or in
Okay.
in the community of integral system or not, which is that's a so-called generalized spectral theory by a Japanese mathematician called Hayato Chiba. Hayatochiba. So essentially, what he is doing is he wants to study bifurcation when the linear problem has the spectrum is already on the imaging axis. There's no spectral gap. So whenever you consider standard, like an NLP setting or Doppler setting, there's no spectral gap. So there's no center manifold reduction.
Yeah.
And then how can you study bifurcation? How can you control the decay rate and something? But then he used a Geyer triple and weaken the topology so that your spectrum is in the complex plane line, but with a weaker topology, now you can consider like a branch of the Riemann sphere. And then in the branch, you can study bifurcation. And now the immediate axis is in the original plane, complex plane. But with a weaker topology, you can study stability or center manifold reduction. Maybe that's a way. I also say this to Jinsei, but maybe this doesn't work. I don't know. But as a dynamical system guy, introducing exponential weight is a little bit artificial, in my opinion.
Okay.
But maybe without this, nobody can do analysis. And also, Jinsei told me there's a stability tool or method of Kevin Zunbrun. Do you know him? Kevin
Zunbrun, yes.
Yeah, and there's also another Korean mathematician, Kang. He also invented something. So, Jinsei, please continue my comment, okay?
Yeah, but Zunbrun and Kang's approach is for the parabolic type equation. So,
Okay.
which is not a dispersive equation. And in terms of dispersive equation, for instance, I think the Camassa Holm is the same. In the usual L2 based space, you cannot expect asymptotic stability because suppose there is a traveling wave, solitary wave with the speed c1, and you consider the different traveling solitary wave with the speed c2, and suppose those traveling speeds are very similar. So in L2 space, initially they are very small. The perturbation is very small, but as time goes on, the faster, the bigger one, which is the bigger solitary wave, travel faster than the smaller one. So in terms of orbital stability, they are stable, but in terms of asymptotic stability, it's not stable in L2 space. So that's true. So introducing exponential weight is just one way to say something about asymptotic stability in this type of equation. Yeah, so currently there is another result by Frank Murray and they do not rely on the exponential weight, but still there's they restrict the domain of function space. So yeah, anyway, yeah. So my point is that in the usual L2 based space, asymptotic stability is you cannot expect asymptotic stability.
Yeah, exactly.
I see.
Yeah. Very good explanation. Also, in the paper by Pego and Weinstein about asymptotic stability for KdV, these things are very nicely explained, and that's the mechanisms are very nicely explained, just like Yunshik just did. Yeah.
Thank you.
Good. So I don't know if there are any further questions. Okay. So if that's not the case, maybe we can close the session here. And